Okay, today we are going to find absolute maximums and absolute minimums. So an absolute maximum is the absolute highest point on a graph. So by definition 1 up here, we see that it says if f of c is greater than or equal to f of x, meaning that if we have a y value at some x value of c that is larger than all the other y values, then this will be called the absolute maximum of f. So we'll look at the second picture below. This picture represents an absolute maximum, where the point 0,4 is the absolute highest point on the graph. So this point 0,4 would be considered the absolute maximum. Okay. And then 2 says if we have the smallest point on the graph, the absolute lowest point on the graph, then that point is called the absolute minimum of f. So picture 3 represents what an absolute minimum is. Here, the point 0,0 is the absolute smallest point on the graph. It has the smallest y value, so this makes it the absolute minimum. Okay, so this is what we're going to be looking for today: absolute maximums and absolute minimums. The first graph does not have an absolute maximum or an absolute minimum. It does have a local max at this point and a local minimum at the point down to the right. It does not have an absolute maximum or minimum because these tails head towards infinity and head towards negative infinity. So there's no absolute highest point. So that's what absolute maximums or minimums are: the absolute highest point, the absolute lowest point. And a fancy name for them is called absolute extremum. Okay. Cool. All right. And we come across our first theorem. A function that is continuous on some closed interval will have both an absolute maximum and an absolute minimum on that interval. So we're going to be looking at a closed interval. Okay. So what that means is, well, let's look at the first picture. We have a closed interval from 2 to 12. So we have taken this continuous function and put it on a closed interval. And by the theorem, if you are on a closed interval, you will have an absolute minimum, which is the absolute lowest point on the graph, and you'll have an absolute maximum, the absolute highest point on the graph. And this happens again on a closed interval, which means next picture, we change the interval up to 410, and that just changes the graph a bit, which changes the max and minimum. So since we changed the interval, the absolute maximum is now at 105, and the absolute minimum is now at 73. And then the third picture, if we change the interval to 48, well, the absolute minimum, the absolute maximum remains at 105, and the absolute minimum will change to 78. And if we change the interval one more time to 3,11, then the absolute maximum actually occurs twice. And the absolute maximum will happen at 105, and the absolute minimum is now at 73, but that occurs twice as well. So what this last graph is telling us is that we can have multiple absolute maximums and absolute minimums on a closed interval. Okay. Any questions so far?
Yeah.
Go ahead, Brian. I'm sorry.
Oh, okay. Sorry, Chris. No, I was just gonna ask. I mean, like, then how can we tell when it's gonna be like the absolute maximum? Like, it's gonna be 105 once it moves, like you were showing us right there, like to 4 to 8. Like, what ties it into that?
Like, how will we actually find those without looking at a graph?
Exactly.
Good question. That comes up next.
Oh, okay, okay.
Cool. All right,
Professor, I had a question.
go ahead.
Can I be excused? I'm not trying to show off, but I have to go to the Spurs game and change some customers.
Philly contest and Spurs game. I'm assuming you won, so you're going to a Spurs game.
No. I'm in the construction business, so I have to entertain. But I will be watching it Saturday.
Oh, good. Okay.
Okay. I'm not
Right.
trying to do it to you, brother.
All right, man.
Okay. Thank you, guys.
All right. So, theorem 2, locating absolute extrema. So to find an absolute maximum or minimum, this theorem is very important. To find an absolute extremum, they only occur at critical numbers or at endpoints of your closed interval. So absolute maximums and minimums only occur at critical numbers, which we find from the first derivative, or at the endpoints of a given closed interval. So this is how we're going to actually find them without even looking at a graph. So we were already answering your question, which means, of course, we'll try it out on the next page. Find the absolute extremums. So we are given the function x cubed plus 3x squared minus 9x minus 7. And we want to find the absolute maximums and minimums on the intervals -6 to 4, -4 to 2, and -2 to 2. So they're giving us closed intervals to find absolute maximums and minimums on. So the very first step is check our domain. We want to make sure our function is continuous. Well, again, you guys get the easy functions. Every function you get is a polynomial. So what is the domain of every polynomial?
All real numbers.
All real numbers. That's great. So for A, our domain is all real numbers. All right, that's always going to be given. Now B, find the critical numbers of the function. So we know how to do this. We take the derivative, we set it equal to 0, and we solve for x. So with that being said, take the derivative, f prime of x, we get 3x squared plus 6x minus 9. 3x squared plus 6x minus 9. Then set it equal to 0. Not that one. Set it equal to 0 and solve for x. Okay. What could I factor out?
3.
3. That gives me x squared plus 2x minus 3 equal to 0. And then we can factor this more, which means that I'll get x plus 3, x minus 1 equal to 0. Okay. Set x plus 3 and x minus 1 equal to 0. And what are my critical numbers?
-3 and +1.
-3 and +1. There we go.
Quick question, Professor. You
Go
are
ahead.
recording, right?
Yeah, I'm recording.
Okay, awesome. Thank you.
All right. These are my critical numbers. So any questions so far? Okay. So now what we're going to do is take the given intervals above and the critical numbers and plug them in to the original function to find absolute maximums and absolute minimums. And we only need the endpoints of the interval and the critical numbers, because that's what the theorem above stated. Absolute maximums and minimums only happen at the endpoints of your interval and at critical numbers. So we'll start with this first interval of -6 and 4. And what we want to know first is, do these critical numbers fit in that interval? Are -3 and 1
Yes.
in between -6 and 4?
Yep.
Good. So when we put our x values down, I'm just going to have -6. I'm going to put them in order: -6, -3, 1, and 4. Those are the only numbers we need. And now we're going to plug them in to the original function. So guess who's going to help out?
Desmos.
Desmos, our best friend. Close that, come here.
Are we using here the the derivative, or are we using the original formula?
The original formula.
Okay.
X cubed plus 3x squared minus 9x minus 7. Do my table, boom, and let's plug these numbers in. All right, we have -6, -3, 1, and 4. All right, so I get -61, 20, -12, and 69. Okay, now look at the y values. And which one is the smallest y value?
-61.
-61. This means that this will be my absolute minimum. Then look for the largest y value. What is that?
69.
That means that this is my absolute max. That's all we have to do. And now we have another interval, -4 and 2. Do my critical numbers fit in that interval?
Yes.
Yes. So again, we'll have -4, -3, 1, and 2. And we are still plugging these into the original function, which means we already know the value for -3 and 1. -3 gives me 20, and 1 gives me -12. We just have to find the value of -4 and 2. So I'll type that over here in Desmos, -4 and 2. I get 13 and -5. Okay. Now look at your y values, and which one's the smallest y value?
-12.
-12. There it is. Absolute min. What's the largest y value?
20.
20. There's my absolute max. Okay. Last interval. -2 to 2. -2 to 2. Do my critical numbers fit in that interval?
Negative.
Yes.
No. Which one does not fit?
-3.
-3. So we do not include it. We exclude -3. So we'll just have -2, 1, and 2. And we know the value of 1 and 2 from the chart to the left. You get -12 and -5. And then we know the value of -2, or we don't. I'll type it in over here.
We don't.
-2 gives me 15. Okay. Now, who's the smallest y value?
-12.
Negative 12. There's absolute min. And the largest y value?
15.
15. There's my absolute max. Okay. And that's how you find absolute maximums and minimums. You'll be given an interval, you'll find the critical numbers, and you will plug the critical numbers and the endpoints of the interval to find your absolute maximums and minimums. Any questions on that page?
Sorry, did you say that we're going to plug in the absolute min and max into the derivative?
No, we plug the critical numbers and the endpoints to find the absolute max and minimums.
Oh, okay.
Into the original function. The only thing we use a derivative here is to find critical numbers, and that's it.
Okay.
All right, everybody good? Okay. All right, next page is the second derivative test for local extrema. Now on this page, we're going to come back to finding local maxes and minimums. Now, if you remember from, Tuesday and last Thursday's lesson, to find local max and mins, we take the first derivative, we set it equal to 0, we solve for x, and then we make a sign chart, we pick test numbers, and we find intervals of increase and decrease, blah, 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 blah. Well, this page is here to make your life easier. It's called the second derivative test. What it does is avoids a sign chart. It avoids you making a sign chart and picking test numbers. So it shaves off some time. So the way the second derivative test works is we are going to take the first derivative and find the critical numbers. And then we are going to take the second derivative, we're going to find the second derivative, and we are going to plug the critical numbers in from the first derivative into the second derivative. And here's where the definition starts. So if we have a critical number and plug it into the second derivative, if the second derivative is positive at that critical number, this means that that critical number will be a local minimum. And this is represented by the chart down below. We know that to find a critical number, you set the derivative equal to 0. And then we take that critical number and plug it into the second derivative. If the second derivative is positive, this means that your graph is concave up, which means you will have a local minimum. Remember that concave up looks like this, and the point will be a local minimum. Okay. 2, if the second derivative is negative at the critical number of C, then you will have a local maximum. So I'll run through the chart explaining number 2. To find a critical number, we set the first derivative equal to 0. And then we plug that critical number into the second derivative. If the second derivative is negative, this means that the graph will be concave down and you'll have a local maximum. So a graph that looks concave down looks like that. And the high point will be a local maximum. Okay. Now let's say that we find our critical number, but then when we plug it into the second derivative, we get 0 as a result. Well, 0 is neither positive or negative. 0 gives us no information. This means we have no idea what the graph looks like, which means the test does not apply. And if you fail the second derivative test, Well, guess what? You have to go old school and make a sign chart. So not all shortcuts work. So if your second derivative test fails, then you're going to have to make a sign chart, pick test numbers, find intervals of increase and decrease, and then find that local max or min. Unfortunate, right? All right, well, let's try it out. Let's find local maximums and minimums using the second derivative test. So number one, given this function, x cubed minus 6x squared plus 9x plus 1, let's go ahead first and find the critical numbers. Which means that I'll call this A. F prime of x gives me 3x squared minus 12x plus 9. Then set it equal to 0 and solve for x. What could I factor out?
3.
3. You get x squared minus 4x plus 3 equal to 0.
Mhm.
And what does that factor to? What are the only factors of 3 that can make 4?
It's x minus 3, x minus 1.
There you go. Which means, what are my critical numbers?
3 and 1.
X equals 3, x equals 1. Do we ever care about this 3?
No.
No. There's no variable attached to it, so we don't care. So these are only critical numbers. Okay, now we move on to step B, which means we're going to take or find the second derivative. So let's find the second derivative, which means our second derivative is going to be 6x minus 12. And what we're going to do next is take these critical numbers and plug them into the second derivative. And let's hope we don't fail. I'll say plug critical numbers into second derivative. Okay, so first up is x equals 3. You get f double prime of 3, which will give you 6 times 3 minus 12, which is 18 minus 12, which gives us 6. And once again, we don't care about the number. We only care about the sign. So 6 is positive. So this means if we follow the chart above, if the second derivative is positive, this means that we have a local
Minimum.
minimum. So what this means is that x equals 3 is a local minimum. And then we have one more critical number to plug in. X equals 1. F double prime of 1 gives me 6 times 1 minus 12 gives me negative 6. So the second derivative at our critical number of 1 is negative. Looking at the chart above, if the second derivative is negative at our critical number, we have a local
Max.
max. So this means x equals 1 is a local max. All right. And that's it. That's how you use the second derivative test. It avoids a sign chart. I don't know how much time that saves, because if it fails, you still have to make a sign chart. So, any questions on that page? And of course, if you needed to find the exact location of your max and mins, you would take these points and plug them into the original function. But that's it, guys. We're done.